Okay, I'm going to start with a video of one of our launches. I want you to notice two slightly unusual things. The first is that this launch is happening in the middle of a field in Texas. So among other things, we have to contend with the cows that run around in circles every time we launch and then go back to munching grass when we're done. The second thing is that this rocket has landing legs, because instead of just going up, it's going to come back down and land where it started. The reason is that we want to make reusable rockets. Every rocket that can put something into orbit currently is expendable. So this vehicle the size of a skyscraper goes up, deploys its payload, and then just falls away and burns up in the atmosphere. This is one of the primary reasons that getting to space is so expensive. Imagine flying a plane across the country and then just throwing it away when you're done. Well, clearly none of us can afford to fly. Instead, we want to make rockets that we can land, just like an aircraft, refuel and refly, and then we think that because propellant is less than 0.5% of the cost of the launch, we can dramatically decrease the cost of getting to orbit. The other reason to make reusable rockets is to go to Mars. And it's no secret that we want to send hundreds of people to Mars and bring them back again. And to do that, you either have to send a dedicated return vehicle, or you send a reusable rocket that you can refuel with propellant that you made at Mars, and then send that same rocket back. Now clearly we're not the first people to think about making reusable rockets, and here are some of the operational vehicles or concepts that have existed in the past. You've got the Space Shuttle, the DCX, the Blue Origin New Shepard, the X-33 Venture Star, and these come in lots of different flavors. You can take off vertically and land horizontally like the Space Shuttle. You can take off horizontally and land horizontally like Virgin Galactic. We choose to use vertical takeoff and vertical landing. And this is for two reasons. The first is we think that it allows for rapid reusability. If you're landing in the same configuration that you launch in, then you just land, refuel, and you're ready to go again. The second is that it extends to other planets much more easily. You imagine if you need a runway to land, then clearly you're not going to be landing on Mars anytime soon. If we can land vertically, we can land almost anywhere in the solar system. So how does this work? Well, we've been focusing on making our first stage of our rocket reusable because that's frankly the easiest and also by far the most expensive part of the rocket. And in cartoon form, the way this works is this. We launch with the two stages, we ascend, we separate the stages, the second stage goes off into orbit to deploy the payloads, and up until that point, everything looks like a normal expendable launch. At that point, though, we flip this rocket around and point it back towards the launch site and do this thing called the boost back burn that turns our velocity vector around and sends us shooting back to the pad. We flip around again, deploy fins, do something called the entry burn that slows us down just before we hit the atmosphere. We fly ourselves back through the atmosphere, deploy the legs, and light the engines one more time for a vertical landing. A lot of people look at this and immediately say that it's crazy. And the reason is they know the rocket equation, which says that to put a small amount of mass into orbit, you have to start with a very large mass of propellant. Now, presumably, if I'm using all that propellant to put the velocity in, I have to take that velocity out again, I have to start with an even bigger amount of propellant, and the whole thing snowballs out of control. The reason why it's not entirely crazy is because the rocket equation doesn't quite apply. On ascent, aerodynamics are hurting us, but on the way back in, aerodynamics are helping us. So we put in about 2 kilometers per second on the way up. Terminal velocity on the way back down is only about 200 meters per second. So aerodynamics on the way back down has done 90% of the work for us. Now, the one thing you can't get away from is this boost back burn. The boost back burn is expensive, that turns the velocity vector around, and by doing that, we do actually take away from our payload to orbit. So it's going to be a strobe in about 3 seconds. Yeah, I'll start the music in a second. So we can't get away from the fact that this boost back burn is expensive, unless you don't land back where you started, and instead you just let the rocket sail downrange, get rid of the boost back burn entirely, and then land on a floating platform in the ocean. And at every part of this, there are big challenges to to overcome. So for this flip, we're traveling downrange away from our target at 2 kilometers a second, so every second counts. We need to start the engines in midair and do precision boost back targeting. You can imagine that if we burn too short, we'll fall in the ocean. If you burn too long, you're going to hit Orlando, which is even worse, depending on your opinion of Orlando, obviously. You need to make the vehicle survive entry with minimal added mass. You need to fly something that doesn't have wings, it wasn't really meant to fly, but still we need to guide it accurately back towards the target, and then do a precision vertical landing on lightweight deployable landing legs. And about a year and a half ago, we achieved our first drone ship landing. This is 8th of April 2016. This is what it looked like. Actually, on this day, we lost all telemetry in the last few seconds, so this video is the only thing that we had to say that this thing was working. It was pretty awesome. It took us a lot of pain to get there, and what I want to talk about today is basically that pain, is the challenges that we had to overcome, and some of the technology that we developed on the way. And we did this step by step. So we started off by saying, let's not try and land on a target, let's just try and land anywhere, but show that we can enter and land softly. This we call soft landing or land anywhere. We do this supersonic retropropulsion burn to slow ourselves down so that we survive entry. We do a landing burn and we land on landing legs. And we did this for the first time on our Orcom 1 launch. So here's the rocket. It's very difficult to get footage of this stuff happening out at sea, so we send a chase plane out with a very long telephoto stabilized lens, and we were able to get these kind of tantalizing images of a rocket re-entering like this under control for the first time in history. You can see it's not tumbling, it doesn't have fins, but it's being controlled with cold gas. And in a moment here, you'll see just the very end of the landing burn. So the surface of the ocean is there. You can see that it's coming down vertically. It's coming down to rest. And this is basically a perfect touchdown. Unfortunately, the camera guy zooms in, gets a little bit overexcited, and completely loses the critical moment of touchdown. And that actually was really important because there was an ongoing bet at work. Some people saying that this thing is maybe hollow. If we can make it survive that tip over, then we can just drag it back and reuse it. And in fact, if you've seen the video continue there, what happens is the rocket does indeed tip over, it does indeed hit the water, and it explodes. That is no way to make a reusable rocket. What you need is something solid to land on. So we developed this thing called the Autonomous Spaceport Drone Ship. It's basically a floating landing platform with a big SpaceX marks the spot in the middle. It has GPS navigation. It has 4 independent thrusters around the edge that hold it in place, accurate to about 3 meters. And it can tolerate pretty high winds and sea state. The problem with this is precision. We have this thing called the landing ellipse, which is basically the 99% or the 3 sigma area where you can guarantee that the rocket is going to land. And for that land anywhere landing, that was about plus minus 25 kilometers. To land on the drone ship, we have to be accurate to plus minus 10 meters. And so it's really just this tiny blip in the middle of this landing ellipse. So what we need is precision landing. And we spent a good 2 years or so just focused on that problem of getting precision. The way I like to think about precision landing is in terms of managing dispersions. And what I mean by that is, even though the nominal trajectory may be well known, it's this black dashed line here, if the winds blow me to the left, I'm going to end up going to the left. If the winds blow me to the right, I'll end up going to the right. And so this gap between the left and the right trajectory is what I call the dispersion. So basically, the bigger that is, the more uncertain your position is. So this is what happens, is that on ascent, the dispersions grow. And in fact, the rocket tries to fly with the winds to minimize the structural load so it doesn't rip itself in half. Outside the atmosphere, the dispersions are more or less constant because there really aren't any unknown forces acting on the rocket. So then your boost back burn is your first opportunity to shrink the dispersions, ideally to the point where you're at a pinpoint at the atmospheric interface. The problem then is that inside the atmosphere, you have lots of disturbances acting, winds, uncertainties in the atmospheric density, and so your dispersions grow again, and that means that your powered landing burn is your last opportunity to bring the dispersions to the size of a landing pad. Essentially, this furthest left trajectory has to move sideways to hit the target, the furthest right trajectory has to move sideways to hit the target too. So the first thing we did to the rocket is to add fins. And what we ended up going with are these somewhat crazy looking things called grid fins. Traditional fins slice through the air like this. Grid fins go through the air kind of like a tennis racket. But you can kind of think about them as lots of little traditional fins stacked up one on top of each other, and they do the same thing in principle. They bend the flow and put forces and torques on the rocket. The nice thing about them is they stow on ascent, so they're deployed here, but they fold up against the side of the rocket for ascent, and that's good because on the way up, they're on the wrong end of the rocket, on the way down, they're on the right end of the rocket, so you only really want them there for the way back down. And what they do is much like a plane. The plane itself produces lift, the wings produce lift, we produce a lift vector from our body here, and so by pitching the rocket up, I can go long, by pitching it down, I can go short, by banking it left or right, I can make the rocket go left or right. And on my dispersion plot, what that means is that whereas before my dispersions grew in the atmosphere, now they stay constant or in fact shrink. And that makes it so that my landing burn now is within striking range of getting this rocket back to the target. I still have to solve this last part though, and in my opinion, this powered landing burn is the most difficult part of this entire problem. And to give you an impression of why, I'd like to imagine trying to balance a rocket like balancing a broomstick on your hand. And in fact, all control engineers start with this thing called the inverted pendulum problem, which is just this. If my rocket starts tipping to the right, then I vector my thrust over, that puts a torque on the rocket that brings it back vertical again. Now, of course, I need to control the lateral position too, and if you've ever tried to do this with a broomstick, you have this very non-intuitive thing where if I'm trying to move to the right, I first have to move my hand to the left, the broomstick kind of tips over, and then I catch it over here. And that's exactly what I do with the rocket. First, I have to thrust in the wrong direction, straighten up, come back to where I want to be, do the whole thing in reverse, and end up at my target. And in the literature, that's called a non-minimum phase zero. I call it the broomstick effect, but it basically makes control design very challenging indeed. On top of that, we're landing on Earth in a thick atmosphere with a long, skinny body that produces lift, and that does something pretty interesting, which is, let's say I wanted to move my rocket to the right. You would think tipping it to the right like this is the right thing to do. Unfortunately, you generate a lift vector that goes to the left, and at the start of the landing burn, that is so strong that it overcomes the effect of thrust. So what that means is, at the beginning, if I want to go to the right, I actually tip to the left. At the end of the burn, I have no lift, so if I want to go to the right, I tip to the right, and in the middle, I can tip right or left, and I'm not going to go anywhere. And so the guidance on board has to know about all of this and plan accordingly. On top of that, take the broomstick you're balancing and make it floppy. We have a rocket that has structural modes. It's essentially as thin-walled and as skinny as it can be without falling apart, because that's what saves mass. Then fill it with two independent slosh masses. We have thousands of pounds of liquid oxygen and rocket propellant in these two different tanks. And if you've ever tried to do this with like a half-filled liter of cola, you get this weird effect where the fluid moves first, or like the outside moves first and the fluid moves second. That makes it super swirly. Add the usual GNC problems of noisy sensors, sloppy actuators, and processing delays. Do this all on board in real time, and then hopefully you can see that this is a control engineer's dream or nightmare, depending on how you want to put it. So how did we learn how to do this? Well, we built two test beds, full-scale test beds called Grasshopper and later F9R Dev. And actually, when I last came to talk here, we were just talking about Grasshopper. This was a few years ago. What these were intended to do is teach us how to do vertical takeoff and landing with all the challenges of the full rocket. They were never intended to go to space. We made fundamental design choices to make the vehicle more robust because it was an experimental vehicle, but they could get us up and teach us how to do those last few kilometers of the landing. Now, when I say these are full scale, it's really difficult to give people an impression of how big these things are. This is basically a 15-story skyscraper that we're flying around full of rocket fuel in the middle of a field in Texas. It's by far the biggest vertical takeoff and landing vehicle ever made. I hope you will come out and visit Los Angeles. You can see the first ever landed stage, and standing next to it is really the only thing that can convince you of it, but hopefully the Statue of Liberty will give you that sense of scale. Now, when we started flying Grasshopper around, it was the first time the media really started to pay attention to this whole reusable rocket thing. And we got some pretty interesting news stories. We were on Jeopardy, the subject of the Jeopardy question. We were on the Today Show. And this is an iPhone app that I can't say for sure is based on SpaceX's Grasshopper, but make your own choices up about that. And of course, there's YouTube. Now, when I was publishing papers, or do occasionally, I'm happy if 50, maybe 100 people cited my work. Seeing 3 million views on a YouTube clip over the space of a week was pretty insane. The problem is you have to deal with these guys. The YouTube commenters are breed unto themselves, or perhaps three breeds. I found that you get the good and or positive. As a control engineer, I love mad stabilization skills, amazing control of a highly complex system, of course, just Elon Musk will love you. You've got bad and or silly. And actually, my favorite is this technically, if not grammatically correct, failed this rocket plant into orbit. And of course, the conspiracy theory. And you would be amazed how many people have dedicated how many comments to proving that this is all computer graphics. My favorite is a guy called Eric Gustin, who thanks us for finally disproving the 1969 moon landings, because only if those had never happened would Grasshopper be impressive, and concludes with kind of hard to argue now, huh? Okay, so we did 12 tests with these vehicles, started super incrementally, starting with just a 2-meter hop, going to 5 meters, doing first hover, landing at thrust weight range 1, testing out sensors, eventually getting to 1,000-meter hops, teaching us how to do those final kilometer or so of the landing. And in the process, there were two kind of key technologies that we developed that enable us to do the power descent. One is something I call dual control, which is the observation that you've got fins on the top of the rocket, and with those you can vector your aero forces. You've got thrust on the bottom of the rocket, and you can vector that. And by combining those two, you get around this broomstick effect. I can essentially put myself in a pure rotation configuration or a pure translation configuration, and by doing that, I can kind of cheat and pick the top of my broomstick up at the top and then move it straight sideways or rotate it without translating it and get around this whole non-minimum phase 0 broomstick stuff. Now, clearly this only works when you've got enough airflow over your fins, but it turns out that is where we really need the best disturbance rejection in our landing burn, and so it works out. The second is something called large divert guidance. And so this is the ability to move that leftmost trajectory to the target, the rightmost trajectory to the target. To do that, the rocket has to move sideways, and it has to compute this on board. So it finds itself at some point. The ground is maybe 2 or 3 kilometers away. The target is over to the side, and it needs to compute a trajectory that gets there as efficiently as possible. And this is us testing out large divert guidance on Grasshopper. Here we've sent the rocket up, we've set it up to the side of the pad, which is down here, and you can see it doing this sideways maneuver and landing back at the pad. Now, I can formalize this large divert problem as follows. I want to find a trajectory that takes the lander from the initial state to the target state, such that, number one, thrust bounds are satisfied, Typically we have a maximum thrust, but also a lower thrust that's very important. You can't throttle down these very big engines more than maybe down to 40%, maybe 20% if you're lucky. No collision with the surface. We want to make sure we satisfy our attitude and velocity constraints and minimize our fuel use, or equivalently maximize our divert range. And this is a very general problem. This is something that had to be solved for the Apollo landers back in the day, and it's a very clean mathematical problem that lots and lots of people have looked at over the time. Now, I claim that out of these two parts, actually, if you take away the constraints, this isn't too bad of a problem. This is really just a boundary value problem where I've got to find a path from A to B. I can fit a smooth polynomial between my initial and target states, and that works. And that's what Apollo did. You can compute that on board in closed form with very simple computers. The problem is that if you try and fly that, you can very quickly get into trouble. So we can either fly subsurface, and this is a real problem. But the trajectories actually do this if you try and use polynomial guidance. We can violate the maximum thrust or the minimum thrust, so clearly I can't produce that much thrust, and if I try and throttle down this hard, the engine will typically shut off entirely. So it's really the constraints that make divert guidance hard. So what we have is a constrained optimization problem. And I've been working with other guys back at JPL on how to develop techniques that use convex optimization to solve this. And briefly, what we love about this is it guarantees finding a solution in a low number of steps, and it maximizes the spacecraft capabilities. So I can say that if the spacecraft can do it, my guidance can do it. If my guidance says that it can't do it, then the spacecraft literally cannot get there. Okay, so many of you will be familiar with convex optimization, thanks to Professor Boyd. But just as an overall summary, the general non-convex optimization is minimizing some general function over some general set. With convex optimization, I have to put the requirements that my function is convex, that my set is convex. But if I can impose those limitations, then I get tons of nice properties. For non-convex optimization, yes, I can apply it to almost any problem, but it may not find a solution even if one exists. You have to come up with a good initial guess. It can converge to a local optimum. There's no guarantee on convergence time, and in practice, it's pretty slow. Now, we use this, but we use it on the ground. When we are coming up with an initial trajectory to get us from the ground into orbit and get the vehicle back to the launch site, we have engineers on the ground tweaking these nonlinear optimization tools to get there. But that's okay because it's not time critical, it's not safety critical. For that, you need convex optimization. It guarantees finding a solution if one exists, doesn't require an initial guess, guarantees finding the global optimum, has hard guarantees on convergence time, and in practice, is very fast. And so this allows us to find solutions autonomously and on board. Now, I have to show some equations in this talk, and to do that, I'm going to switch to the work we did at JPL. So this is not SpaceX work, but this is stuff that's in the open literature, so I recommend you go and read the papers. What we did there is, for Mars, the atmosphere is thin, so the dynamics are almost linear. The key challenge is the non-convex thrust constraint that says that I can point thrust in any direction, just don't go above a max thrust and don't go below a min thrust. And that's fundamentally non-convex. So there's a technique that was pioneered by a guy called Betcher Chignacher, who's now at the University of Washington, who I was lucky enough to work with. And we call it lossless convexification. The idea is you take something that's not convex, you do some mathematical tricks, you turn it into something that's convex. Now I can use a standard convex solver and get all those properties that I talked about on the last slide. So what does that look like? Well, this is the formal definition of our Mars landing problem. We want to minimize propellant usage, which is an integral of our norm of thrust. Rigid body dynamics. By propellant depletion means that I lose mass over time. Don't hit the ground, don't run out of propellant, start where you start, end where you want to start. And then importantly, these thrust bounds that say don't go above this max thrust and don't go below this minimum thrust. And what the lossless convexification does is it takes that and relaxes it into a convex problem. So you introduce this slack variable gamma which is going to become a proxy for the norm of my thrust. I put that in here, and then I relax these constraints here. So this is now a convex constraint. In pictures, what that looks like is this. So let's say I was just planning it in 2D, then I'm allowed to pick my thrust anywhere in this 2D donut. I can point my thrust vector anywhere, but don't let it go below this throttle value or above this throttle value. That's non-convex. I lift it into a higher dimensional space by adding this variable gamma. Now I have this convex space here, which is a superset of this set here, but this is convex. Then I solve that relaxed problem, and the key theorem here says that the solution to the relaxed problem is in fact the solution to the non-convex problem. So you took a problem, you magically made it relaxed, and you showed that it solves the original problem. Now, when I first saw this, I was, kind of blown away. Like, there's no way that this can actually work. There's a whole bunch of Pontryagin minimum theorem that goes along to prove this, but the intuition is really simple. Basically, what the relaxation is doing is saying, in the relaxed problem, you're allowed to throttle down below 20% or below 50%, but you have to pay the same regardless. And given that, what the optimizer does is say, well, if you're going to charge me for 50%, then I'm not going to use 0. I may as well use 50% to get to the target as quickly as possible. So that's really the way that the Pontryagin maximum principle allows us to prove that this gives us the global optimum. So this is pretty cool. Unfortunately, when I got to SpaceX, I realized that this doesn't actually work for landing our rocket on Earth. It's a fundamentally different problem. We're a lifting body in a thick atmosphere. That makes the dynamics very nonlinear. We've got the control reversal that I mentioned. So we don't use G-fold that we developed at JPL, but we do have an in-house problem, an in-house approach that we tailored to solve this specific landing problem. And in fact, we use Stephen Boy's CVX gen code to do a very high-speed customized convex optimization on board. That's what we've used to land all of our successful landing attempts, and the non-successful ones as well, but none of them. Okay, so at this point, we were ready to try our first precision drone ship landing. And we tried this a few times. The first time out was the first time out with the fins, and the first generation of the fins had a finite supply of hydraulic fluid. And so if you misestimated how much total motion you were going to need on the fins, you'd run out of hydraulic fluid. That's exactly what happened. We lost control of the rocket at the start of the landing burn, and this is what happened. By the way, it was my job to figure out how much hydraulic fluid we needed. The second time out, we added hydraulic fluid, and we executed a perfect landing exactly where we wanted to be. Unfortunately, there was no drone ship out there to land on because the weather had been so bad at sea that day that it couldn't stay out, so we upgraded the drone ship, and for the CRS-6 landing, I was utterly convinced it was going to work. And here we have a zoom lens again, same camera guy. You'll see he zooms out this time instead of zooming in. But when the landing burn starts, you'll see him zoom back in and get a good shot. So here, we're controlling with the fins, we're steering our lift vector, the rocket is right there, and then you'll see just a spot of light when the landing burn starts. Right there. And so now the rocket is doing its computer trajectory to the target, the drone ship, which is right beneath it. It's doing dual control with the gimbal and the fins. And you'll just see a small wobble of the thrust vector right about here. And that's where the main throttle valve got stuck. It destabilized the rocket, and even though it came back, it wasn't in time for us to recover. We didn't quite nail the lateral velocity at touchdown. With the legs break, the rocket goes over, and this is what close but no cigar looks like in our world. Even worse than that, our next time out was our CRS-7 mission, and losing a rocket on landing is acceptable, but not losing it on ascent. That's what happened with CRS-7. We lost a NASA payload on the way up. So the company has to then go into kind of take a step back understand what happened. We were down for about 6 months. And that meant that our return to flight was not only the return to flight for the entire company, not only our next chance to do our first ever landing, but we decided to go for broke and land on land back at Cape Canaveral. And this is what happened. You did get the news from the straight line start.
Propulsion is still nominal.
Stage 1 entry 7. This wasn't an experiment. This is with real paying customers, and that's what you're seeing here. That's reporting the customers to orbit. So that was a pretty good day. And when I was doing my post-flight data review, I wanted to show a trajectory from start to finish that we'd actually flown. And I put the landing target on there and couldn't see it, so I zoomed in and couldn't see it, and zoomed in and couldn't see it, and then finally, when you get down to the last 500 meters, you can see how big the pad is that we tried to hit. And that kind of really made me feel good that we managed to hit this thing from 200 kilometers all the way down to the ground. What you end up with is one used rocket. This is the first one back in Cape Canaveral. Amazingly, this thing was in pretty good shape. I mean, this leading edge is the funkiest looking leading edge of the entry vehicle you've ever seen. But the nozzles are actually okay, apart from some kind of cosmetic dirt here. The paint has some problems, but apart from that, it's actually, looking in pretty good shape to fly. Shortly after that, we landed on a drone ship for the first time, as you saw at the beginning. These are the guys that pulled it off the drone ship at Port Canaveral. Quickly, we had 2 used rockets, 3 used rockets, 4 used rockets. The announcement for this talk said 19 landings. Because it's a month old, we're now at 21 landings. And it's kind of amazing how we went from that many failures to kind of cranking these things out, which is pretty awesome. I spoke a lot about guidance, navigation, and control technologies, but there's lots of other things on this rocket that we had to do to make this work. The landing legs are pretty awesome. They're about 99% carbon composite biomass, which makes them very lightweight. They fold up to a very small form factor for low drag on ascent, and then give you this wide base at touchdown. The grid fins I mentioned, aside from being able to stow and deploy, they're very nice in terms of actuation moments. The amount of torque you need to apply is very low, because for a traditional fin, the center of pressure moves a lot between hypersonic and subsonic speeds, so you can't put a single hinge point where those moments are going to be minimized. With the grid fins, because you have such a short chord length, you have low moments all the way through the hypersonic to subsonic range of flight. Fast throttling engines, this is critical for precision landing close to touchdown. We can throttle down pretty deep, about 40%, and we can do that very quickly. And there's this thing, supersonic retropropulsion, I mentioned briefly. This is for the entry burn where we slow ourselves down before we hit the atmosphere. And this is this very aerodynamically interesting phenomenon where you're shooting out a supersonic flow into an oncoming supersonic flow, and it's something that's very difficult to predict in CFD or in a wind tunnel. And this is what it looks like. Here you're looking up at 3 engines at the bottom of the rocket. Here's the side of the rocket. And you get this crazy kind of Eye of Sauron pattern here. No one's really been able to explain adequately to me. You'll see when we go down from 3 engines to 1 engine, it kind of shrinks into the circle here, maybe a 5-pointer star or something like that. I mean, just really, really interesting things. Not only from a purely kind of curiosity standpoint, but this is something where if we can perfect this technique, NASA is actually very interested in using this to land very heavy payloads at Mars, because the existing parachute technologies really don't scale too much beyond the ones that we've already used at Mars. So we collaborated with them. We sent out, or they sent out their aircraft to go and make infrared measurements of these plumes and got some great data for it. Okay, so what have we been doing since then? The key answer is pushing the envelope. Those first landings that we did were pretty inefficient. We did everything very slowly. We had extra propellant for everything. And now really what we need to do to make this practical is to be as efficient as possible. And what that means is if we can be more efficient, we can maximize the fraction of missions that can be recovered. So if someone gives us a really heavy payload to go to a high orbit, I still have enough left over in my rocket to do the landing. I can minimize the number of landings that need a drone ship because I can afford to do the boost back burn more often. And it can reduce the stresses on the rocket during entry for reusability. To do that, I need to reduce my landing and boost back burn propellant, and there are 3 examples of how to do this. I'll talk a little bit more in detail about the fast flip and the 3-engine landing burn, but also we can do aerodynamic braking maneuvers that we're getting into more recently. So what's the fast flip? Well, if I go up and then do a very slow, leisurely flip, I've gone way down range before I start my boost back burn, and I need to do a very long and expensive boost back burn to get back. If instead I can do a fast flip, I can get my velocity back towards the landing site more quickly, more performance to put into orbit. So in July of 2016, we did that for the first time. Here's actually one during the day. You can see the first stage kicking over with coal gas thrusters, and then you'll see the engines light for the boost back burn. There's the second stage going off into orbit. Here's the first stage coming back towards the landing site. And at night, you see this crazy plume interaction between the second stage and the first stage. This looks really awesome in person. I would really like someone to study what the hell is going on here, but you know, it works for us, so we don't have the time to care about it more than that. The second thing is the 3-engine landing burn. So you can imagine that if I start really high up and do a really slow landing burn, that is less efficient than if I wait to the very last minute and slam on the brakes as hard as I can. So we do that with a 3-engine landing burn. We start much lower, about 1 kilometer instead of 3 kilometers. Shut down to 1 engine for the final part, but this allows us to save a whole bunch of propellant, and we did that in May of 2016 too. And of course, we had to actually show that these things are reusable. And so in March of last year, we did our first reflight. Some people call them used rockets, we call them flight-proven rockets. And that rocket that you saw landing on the drone ship at the very beginning, that was that CRS-8 landing, it became our SES-10 launch, and then we landed on that mission as well, showing that you can do the full recycling process. So since then, we've been upping the tempo. We launch every 2 weeks now. That's given a lot of challenges in automating the process. At the very end of last year, we did something that I particularly enjoyed, which is freaking out celebrities in Los Angeles. And so it turned out we got the lighting just right and flew down the western seaboard of California on a Friday night in full view of Hollywood. And so Jaden Smith was convinced it was a UFO, Demi Lovato, and so on. And if you just Google UFO Los Angeles, you will see tons and tons of really fun videos taken by amateurs of this effect. But the big thing coming up is Falcon Heavy. And this is a very recent shot of it vertical on the launch pad for the first time. Falcon Heavy is 3 Falcon 9 first stages strapped together with a second stage on top and then a payload. This is the rocket that is first, for us, going to be able to send something to Mars. So very exciting. Particularly exciting for me is that we're going to try and land all 3 cores essentially at the same time. So the 2 outer cores are going to flip around and come back to the landing site at Cape Canaveral. The second core, which burns for longer, comes down and lands on a drone ship. Those will happen almost simultaneously. The second stage goes off into orbit. And this will be really, really cool if it works. But from a practical standpoint, what this means is that as a fraction of your rocket that you're reusing, you've really got a very, very capable rocket where something like 80 or 90% of the overall cost of the rocket is reused. And that will be great. Our first flight is hopefully coming up before the end of the month, although nothing's guaranteed in this game. Because it's a demo flight, we don't have a paying customer that's going on top. So Elon decided to send a cherry red Tesla. So this will actually be going into Mars distance orbit. It's not going to get to Mars, but it's going to be in the same distance as Mars orbit is, on like a 1 billion-year trajectory or something like that. So stay tuned for that. It's going to be exciting one way or another. So I'm going to leave you with one more video, and that is how not to land an orbital rocket booster. convince you that doing this stuff is hard. If not, please feel free to try your hand at this incredibly infuriating web game that some guys at MIT made. At least the internet has decided that this is a very, very difficult thing to do. With that, please, if you're interested in coming to work for SpaceX, we are hiring in all fields. I'd love to get any resumes or anything, chat to some of you guys. With that, I'll take questions. Yeah.
All guys did. Comparing this for coming back to Earth, how is this efficiency-wise versus aerodynamic landing like Space Shuttle Buran or any other efforts?
Yeah, the problem with an aerodynamic landing is you have to add a system, the wings, that is specifically for landing. So the reason we like vertical takeoff and landing like this is you already have the engines there. You already have that mass for takeoff, you use exactly the same system for landing. So kind of my job was to take something that was optimized for launch and add the minimal set of things that makes it land. And so the fin, there are some other things I can't really talk about, but the fins are the most visible thing. The fins of the legs are the most visible thing that allow this thing to land. Given that, it actually ends up being, I believe, more efficient to do vertical takeoff and landing. You end up with something that's highly optimized for ascent instead of something that's kind of a mishmash of a winged vehicle and an ascent vehicle. It's hard to make direct comparisons with shuttle because shuttle was also a human-rated vehicle. So it had all these other constraints that kind of handicapped it. If you look at the history of the shuttle, it started off as one thing, ended up as something completely different. So maybe a clean sheet design would win, but I actually still don't think so. And of course, landing on a runway is something that we're not going to do on Mars, so this is the way we went. Yeah.
Do you need data and sensors for the amount of fuel quantity during landing?
We do have those, yeah. I mean, in particular with these rockets, you have two, you have an oxidizer and a fuel. And so controlling, you obviously don't want to burn out of one and then have too much of the other one left. So we have control that makes sure that those mixtures are correctly controlled.
Does the weight make a difference too?
The acceleration, the G's that it's in?
Well, but the weight, I mean, you have to support the weight of the rocket and the fuel during landing.
Yeah, right, exactly. Yeah. We use the information, we say that. No, yeah, we use the fuel mass. Which I guess more about, yep.
Is there enough of an atmosphere on Mars to use the fans, the fins in the same way when you're landing?
I mean, so we are working on the Mars vehicle now. Fundamentally, it's a different problem. I would say that the biggest thing is that this is a suborbital vehicle. The first stage never gets to orbital velocities. So when you're bringing something back from orbital velocities, or when you're entering at Mars, you have much higher heating. You know, we don't have much of a heat shield, but you typically need a big blunt heat shield to survive that. So we're going to end up with something that, yes, it probably will use aerodynamic devices, but it will look totally different. I think the Mars vehicle is going to have a booster in a second stage, and the booster is going to have many things common with this, but the second stage is going to look quite different. All the way back.
So with the advantages that Mars brings with lower gravity and thinner air, do you envision it being like a central hub for spaceship and satellite development? Is there that big of an advantage or something like that?
I mean, first of all, actually, not having atmosphere is not necessarily an advantage. Lower gravity is, but you haven't got atmosphere, so when you've got 1/100th of the density at ground level, and so the air that we can use to slow ourselves down on Earth, we don't have at Mars. Now, on the other hand, you don't have winds, which helps us for landing. So there are kind of pros and cons with both. In terms of being a hub, the question is, where are you going to go from there? I think a lot of people have, by the way, this is not my topic of expertise, but I think a lot of people have spoken about the moon as a hub because you get out of the gravity well of Earth, and then it's easy to lift off from the moon and go elsewhere. I haven't heard people talking about Mars in the past.
Yeah, so the first word in your job title is entry. That entry burn is not needed to slow the vehicle, right? It's needed to protect the outside engines. Your ballistic coefficient's low enough, you're going to come to slow down enough if you can survive. And so my question is, the bottom of the new Shepherd has got it's fared in, and you guys are exposing your engine bells. And I'm wondering if you can say anything about that decision and why you picked the way you did and how you did it for VFR.
Is no the quick answer? Is no, I can't say anything about it. No, I mean, I would say that there are definite things that aerodynamically would be interesting to do. I mean, I think it's really awesome to see Blue Origin, as another person trying to do the same thing, coming up with a different approach, and it's cool to see two different ways of doing it. The entry burn that we do does take away some performance, but the way we look at it is, first of all, let's start with a really long entry burn that makes it really easy to survive entry, and then let's just incrementally chip away at that to make ourselves more and more efficient. And I think all the way through this, it's like push the envelope, get flight data, and what you realize is that actually a lot of, if ahead of time you said, what is the first thing on the rocket to fall off when it re-enters, it's very difficult to predict that. But then you go and re-enter and you just say, oh, 99% of it survived, this thing fell off, so let me make that bit stronger. And now you've got a rocket that is marginally heavier than it was before, as opposed to something like the space shuttle, which some would argue was over-engineered to have like 10x margin everywhere because failure was not an option. Here we have the luxury of going out, it didn't survive entry, okay, let's figure out why not. Yes?
So you mentioned that landing on Mars is a new problem. Did the new constraints affect your ability to take your non-convex problem and turn it into a convex problem? Or is that part pretty straightforward for Mars?
So the work that I did at JPL was for Mars.
Okay.
Yeah, that was for Mars, and that works because there's no atmosphere. It also works because you have kind of a capsule-style lander. And so what that means is that you can rotate very quickly and kind of arbitrarily point your thrust vector. That's different with this gimbaled rocket that you kind of slowly have to snake around all over the place. So that's why we had to do something fundamentally different here. I think we'll have to do something different again for Mars when we land our rocket on Mars, but it's just a different problem from the Mars Science Lab, Curiosity rover type stuff. Yeah.
The last Iridium launch had the grid fins, but not the landing legs. Can you say what you accomplished with that configuration?
No. Sorry. Yeah.
We've heard speculated that you might be trying to land back on the launch mounts.
Yeah.
Is that something you're trying to prove, like that level of precision with Falcon 9, or is that something you're just going to work on later?
I personally think it's going to take. So the idea here is that currently we land on the landing pad. The landing pad is close to the launch site. That's great, but you still have to get a crane, pick it up, put it horizontally, drive it over to the launch pad, put it up again. If you really wanted to get aircraft-like operations, you would just land in the launch mount. Let me go back to the heavy picture. So the launch mount is this thing here. So if you could settle the thing in here after launching it, then you would just refuel it and fly it again. I want to see more people laughing in the audience. Yeah, why not? So that's a very challenging problem, and I think that's what we're going to be attempting to be doing with our Mars vehicle, as Elon has mentioned. I think it's going to take fundamentally different hardware to do that. I don't think we'd be able to do it in Falcon 9, but I would say the Falcon 9 experience showed us what we would need if we started a vehicle from scratch. That's exactly what we're doing with this Mars vehicle. So it's kind of like useful experience without actually proving that we did it. Yeah.
So you mentioned, so given that landing on Earth is a different problem to the Mars problem that you saw, how many techniques were you still able to use related to convex relaxation?
Yeah, it's kind of too much in the weeds. We use a convex solver. We use convex optimization. We use high-speed auto-generated code. It's just a different formulation. That's really interesting.
For the drone ship landing, you have to estimate and predict the position and attitude of the drone?
Drone ship, yeah, good question. So the answer is no. We basically say that the drone ship needs to go to point X and the rocket has to go to point X too. And we rely on both of them being in the same place. And we found that there is some drift on the drone ship, there is some inaccuracy in the rocket, and when you RSS them together, it's enough that you're going to hit the target. Now, the tilt, the question is, what would you do with that if you knew about the tilt? You know, would you try and fly the rocket in and tilt it over so that it landed? You know, it's not clear to me that actually helps you. Instead, we do a passive thing where the drone ship, and this comes from kind of like oil technology, you fill the thing with water, you sink it down very low, and then it just passively becomes very stable. Now, it's possible that the waves are so bad that it's rocking so much that we can't land. We treat that as something called a launch availability constraint. So, you know, we won't launch this rocket if it's too windy. We won't land the rocket if it's too wavy. Our job is to build a rocket that can land in 99% of days. And on the 1% of days, probably a crew doesn't want to go out there anyway, for safety's sake. Yeah.
Can you give us any updates on fairing recovery?
I actually don't work on fairing recovery. It is being pursued, but I don't work on it. Yep.
So you said that you started with Grasshopper, and then you probably started somewhere slightly smaller. Can you talk at all about that?
I wish we had, I guess. We started with Grasshopper. No, and that might sound crazy, but there were lots of debates about whether to start smaller. The thing is that essentially we made Grasshopper out of spare parts. So we had a tank lying around that had been used for structural testing, refurbished it and turned it into a rocket where you didn't need to build a custom part. And I actually think one of the lessons learned is that the danger of test beds is you can spend too much time making a custom thing that is actually orthogonal to the real problem. By taking something that was essentially free for us, we stuck on some legs in like a post hoc kind of way, and then flew it real size, and to deal with the real challenges of loading that much propellant. I think it actually did help in the end, even though, you know, this was like my first 6 months at SpaceX, and flying something that big around in Texas was pretty nerve-wracking. Yeah.
What's the importance of simulations in your process?
Yeah, I mean, we use them everywhere. I mean, we have our in-house simulator. We develop models. We refine them in the sense that when we fly, we get aerodynamic data. We feed that back into our models. You know, we estimate probabilities. I was talking to some people earlier about the regulatory agencies rely on us saying that we have a 99.9999% chance of not causing an explosion that could endanger any buildings or any population. So yeah, we use them everywhere. Yeah.
When did you first develop an interest in controls engineering, and what drew you to the field?
Yeah, I mean, for me, I don't know. For me, it's like the intersection of maths and reality. You know, it's where you get to understand the dynamics of the way things work, and you get to control things. I mean, you get to fly the rocket around. And for me, like, there's nothing more fun than having the whole team at SpaceX build this awesome vehicle, and then you get to go in and write the algorithms that fly it, decide where it's going to fly, how it's going to land, what it needs, you know, to be able to land better. So I was always interested in space, got interested in control pretty early on, and this is like the mix of the two. Yeah.
Can this land in inclement weather? Because you've done this, you've determined all the like perfect blue skies, glowing.
What?
I mean, like, what if it rains or there's some extra wind picks up while it's out?
Okay.
You're just gonna fly it around until I'm waiting until the storm passes.
The drone ships are shown live. Next time, take a look at the drone ship video, and you will see that thing in the high seas, rocking like this, and the flag blowing. Like, we've landed in super inclement conditions. And actually, the rocket knows where the winds are ahead of time, and so. Didn't we show you the video earlier? Right, where it like slides in sideways. So basically, yeah, we've landed in very high winds. That only works because the rocket knows the winds ahead of time, and it uses those to like slide in at the last minute. Yeah.
What percentage of your design process is from known variables, and how much work you have to do thinking of things that are outside of the scope of the simulation that might go wrong?
Yeah, I mean, we try and predict as much as we can. We try and run tests, like wind tunnel tests, to understand what to put in the simulation. You know, simulation is only as good as the models that are in it, so we have to make sure we have very good models. And then we hope at the end of it, when we fly, we were wrong by some amount, you know, and so we all go into our simulation and say that this is the parameter I think could be wrong, let's vary it by plus minus 50%, and then you hope you're right. And sometimes you're very wrong, and you just have to go and learn that and fly it. Right. So I think the great thing about this program is that these stages we're going to burn up in the atmosphere anyway. You know, we get to go out and fly, no one will lose anything if we do get it wrong, and by the time we've flown enough times, we know all the things we don't know yet. I will say that there are still some really interesting things to do with the interaction of supersonic flows when you have an engine going faster than Mach 1 or close to Mach 1, but we really still don't understand why they're there, but we can observe them, put them back in our models, and learn to fly with them.
Yeah, so you have talked about trajectory planning and using convex optimization to solve that problem. How about, can you say a little bit about feedback control?
Yeah.
What approaches and technologies you use for doing that?
Yeah. We tend to favor frequency domain, single input, single output work. I disappoint a lot of people when I say that. And all I encourage, I think, grad students and undergrads is that there's tons of intellectual depth there. And I think I learned a lot of more advanced stuff in grad school, and then when I went into industry, I had these, old experts kind of like teach me, like, no, you really have to be good to understand this stuff deeply. And so we start with the PID loop, and we build it up from there. We do loop shaping, it's kind of industry standard stuff, but it is actually difficult, and it works really well. All the way back.
So, how accurate do your physical models have to be to be able to land a rocket successfully? Do you have a lot of difficulty getting your physical models good enough at the point where you can actually land it?
Yeah, it just totally depends on the system. I mean, the engines, we test them on the ground all the time, so we know those pretty well. Aerodynamics, notoriously difficult to get these hypersonic models right. Very difficult to test wind tunnels with a jet engine or a rocket engine shooting out in the middle of the wind tunnel. So it just depends on which one. And then you have to size the vehicle appropriately. So if your aerodynamics are very uncertain, then you've got to make fins that can take out those uncertainties. So yeah, they vary highly across the system. Yep.
So with the obvious grain of salt that neither ULA nor DLR landed a rocket yet, they've published papers talking about their analyses more on sort of the economic side of using it. And the big conclusion that they come away with has been consistently that they think that it doesn't make a whole lot of sense performance-wise to land on land versus on a downrange platform. But it sounds like the big push really is to move more towards landing on land. Sort of what's the difference in thinking?
Yeah, and I think what a lot of those analyses miss is how discrete this problem is. And what I mean by that is if a customer comes to me and I get to scale my rocket to that payload, then yes, it wouldn't make sense to use all of this additional propellant. Like I could just make the smallest, cheapest possible rocket and then send that thing into space. The thing is, we have a rocket. You know, every company has a rocket. And so when a customer comes to me with the heaviest possible payload, I probably won't be able to land it back at the launch site. But the majority of them will come to me with something that's like half that heavy or 2/3 that heavy. Why not then bring the thing back to the launch site and get very fast turnaround? Don't spend money on a drone ship going out to sea. Don't have that delay. So I see reusability and return to launch site as a way to kind of use up excess capacity in your rocket. You know, you build your rocket to the heaviest thing on the market, and then anytime you have excess, you just use that in a kind of graceful way. I either go downrange, it's kind of annoying, but at least I get to recover it. I go return to launch site, that's awesome. Yep.
How much time data and model extrapolates to VFR? And will you need a VFR test bed?
Lots of it does for the suborbital part of it. So for the booster, tons of that does extrapolate. For the orbital vehicle and the vehicle that's going to go to Mars, there are some things we learn, but the aerodynamics will be completely different. So it's possible that we end up with a test bed there too.
You mentioned everything being a GPS guidance. Considering you're going into lots of precision landing, did you ever consider some other form of guidance system?
What would you suggest?
Like an instrument landing system, like an airplane sends out a radio signal directly where it is, and then you have relative position instead of absolute position.
Yeah. So we looked at relative positioning, but to hit the pad, 10-meter accuracy, GPS is going to do just fine. I think if we're talking about landing in the launch mount, we might have to start talking about relative positioning. You see a lot of guys using relative positioning, like Mastin does these kind of relatively small hops and uses relative positioning. It's difficult to do that. You have to maintain a link between your ground station and the target the entire time. If you're going outside the atmosphere, coming back in, plasma, and all this kind of stuff, it's very easy for you to lose rock on your vehicle, and then that will make your filter go unconverged, and it will take you like minutes to get back to a converged state. So we just don't need it. We are looking at what's going to be the next step with landing the launch mount.
There was a video of the VFR transporting people across the plane. I'm not sure how serious that was, but I'm just curious about how shaky these are on the way down, and if that's something that can be made in order to actually comfortable for passengers. So what was mentioned is that our VFR rocket could do point-to-point travel. So I think it was like London to Tokyo in like 45 minutes or something like that. I mean, if you look at a rocket launch, astronauts train for a long time so they can take very high Gs that suddenly go down to 0 Gs, and then when you re-enter, you see very high Gs again. So I think, comfort will be a topic. Let me put it that way. You've already asked one. Sorry. Anyone else? Yeah.
Talk a little bit about your like the forensics. How do you figure out what went wrong when your station
I mean, we have telemetry that gets sent back. So even if we lose the rocket, we have a lot of data from a whole bunch of sensors, temperatures, propellant levels, things like this, and then it's just a big, it's a big forensics game to figure out what happens. And I think the end goal of that is to be able to say, this valve got stuck, put that in my simulation, and then recreate exactly the failure. And that's what we were able to do in the case of that sticky throttle valve. We thought, okay, this throttle valve looks like it didn't track properly. You put it in the simulation, it matches what happened in flight, and then you say, okay, this is root cause. There's nothing else here. It wasn't some kind of cascading failure. So we've had to do that, unfortunately, a lot of times. But that's basically the process.